Okay, good morning. Thank you for inviting me. I'm delighted to be here. And as John said, this is one of my favorite topics to talk about networks, both on chip and off chip, and specifically talk about some of my more recent experience at Groq, which is, as John pointed out, in the area of machine learning, which is kind of right at the nexus of HPC and machine learning. So it'll be kind of hopefully you'll find it interesting as I walk through some of the design trade-offs of our most recent ASIC. We are a startup company, and we are just coming out of stealth. So I hope to talk a little bit about what Groq is in the process, so that everyone can learn a little bit about Groq. We were founded in 2016 by a group of Googlers that came to work on the TPU project at Google, and the CEO is Jonathan Ross, who had his claim to fame being he started the Google TPU project while he was at Google, working on a 20% project to see if we could bring to bear some machine learning from essentially a domain-specific architecture. So as we go through this, keep in mind that we're hiring, so hopefully this will be both interesting and timely information. And I would encourage you to look at the Groq website and find out if there's opportunities available for you. So a little bit about Groq. As I mentioned, we're a startup company. We're just releasing our first product, which is it's called the Tensor Streaming Processor, and I'll talk in more detail about that. But we're excited to kind of be finally shipping product, and our first silicon actually was A0 silicon, which means we're able to ship without any additional ECOs or additional spins to the ASIC, which is both kind of rare, but it's very exciting to do. This is the 14th ASIC that I've worked on in my career, and it's been kind of an interesting journey. So I hope to share some of that with you in the process, and talk a little bit about our architecture to give you a background about Groq. So by way of introduction, let's start by looking at the Tensor Streaming Processor at a glance. The TSP is a streaming architecture that's based on this concept of kind of a spatial architecture, in that we have several functional units on the chip that are interleaved with the memory units. In particular, we've got a vector processor sitting at the bisection of the chip, right in the middle of the chip. And then we've got two hemispheres of memory, an east hemisphere and a west hemisphere. And we've got these deep learning matrix multiply units. We call them the MXM units on the east and west hemisphere at the edge of the chip. At the bottom of the chip here, we have our instruction control unit. And this is what's responsible for all the instruction, as you can imagine, instruction control and dispatch of instructions on the chip. And it has a PCIe interface for interacting with the host, and we'll talk a little bit about some of these I/O blocks around the top as we get further into it. But just as kind of a thumbnail sketch as to the layout and organization of the chip, I wanted to just kind of lay this out so that you kind of get a sense of how the different functional units are interleaved and woven together, because I'm going to talk about how we exploit that as we go forward. So I want to point out this is a practitioner's perspective. I've been involved in the academic community for the past several decades, and I've been a practitioner both at Cray and at Google, and now at Groq. And I'm really delighted to bring to bear some of the trade-offs that we had to make in the process to be able to not only inform but to teach and help people understand the architecture more as we come out of stealth mode. So some of the key ideas here I hope to get across is really a couple of main points, and that, relatively speaking, ALUs are very inexpensive. It's the on-chip network, and specifically the wires and bandwidth that feed them at full bandwidth that become expensive, and that wires don't typically scale as transistors do. So we're focused on extracting as much computational density from the underlying CMOS that we can. And so that entails both integer and floating point performance. So we'll talk a little bit about that. Again, the design is really focused on batch one performance. So the design trade-offs that we made for the on-chip network as well as the off-chip network had to support that overall design goal. So it provided both a low latency inference as well as a floating point numeric, so that we can do fast to converge training in low batch numbers. And then lastly, just exploiting the locality and wire density available at the different layers of the packaging hierarchy and how that really drives the packaging constraints for the off-chip network. So let's start by talking about the on-chip network. And I like to kind of talk a little bit about the on-chip network in terms of some of the unique features about the Groq network. And one of the first ones that I'll point out is that we're routing tensors and not packets. So let's talk a little bit about the goals. First of all, on-chip networks have very different constraints than off-chip networks. However, they have many common goals. In particular, we want to exploit the amount of on-chip wire density. That is the amount of I/O pin bandwidth, the amount of ASIC bandwidth that the wiring density admits for on the ASIC. And take advantage of that and understanding kind of the technology parameters that limit or constrain those environments. And one of them is the on-chip topology. And we'll talk a little bit about how we have different kind of topologies per different functional units. One of the constraints that we had to deal with was obviously silicon area. We have a finite amount of silicon. This chip is about a 725 square millimeter chip, so it's a large chip. It's a reticle sized chip. And like I said, we're really trying to exploit the abundant amount of wire density on the chip, as well as provide a low cost network for off-chip networking as well. So as we go through this, I'll talk a little bit about some of the trade-offs in terms of reliability and yield and how we had to accommodate for that in the design. So let's start by looking at kind of a very traditional approach to dealing with kind of on-chip networks. And let's look at a typical 2D mesh of a many-core architecture. And in this arrangement, we've got each core is a heterogeneous core, in that it consists of an integer unit for fixed point, a floating point unit for floating point arithmetic, obviously, but it also consists of a load store unit for doing memory references, interacting with the memory, and a network unit for interacting between the cores and among the chips. And what we did is we rearranged this 2D mesh into a two-dimensional organization that exploited the heterogeneity of these different functional units. In other words, we took the homogeneity of this functional unit and disaggregated it and spread it up across the chip. So we have our integer and floating point units here sitting on the edge of the chip. We've got some network functionality that provides us with data reshaping and ability to kind of move tensors around, move elements of the tensor around. We've got a memory system that corresponds to our load store unit, in particular being able to store results and retrieve operands from memory. And like I said, this concept of a functional unit is this notion of a functional slice, where you've got these functional units of the same type that are organized as kind of a stack, a vertical stack on the chip, that together form a single SIMD execution slice. And each of these slices has their own independent program execution, and the instruction, the ICU performs the first several stages of instruction decoding and dispatches the instructions as they start to flow on the on-chip network and are executed in a cycle-by-cycle manner as they flow on the chip. And we'll talk a little bit more about this, but I wanted to just kind of break this apart and talk about it kind of in a first principle sense. We started by breaking up the traditional 2D mesh and treating it as a kind of hybrid 2D mesh. And I'll talk specifically about what we did kind of to make it more domain specific. So as I mentioned, it's kind of hybrid in that we treat the two dimensions somewhat differently. In particular, we have the bulk of the data flow happening in the X dimension, in other words, in the eastern-western dimension, and the Y dimension is responsible for instruction fetching, as instructions flow southward into this instruction control unit and are dispatched north on the chip. So these functional units consume the operands from stream registers and produce new results. And we'll talk about this more. This is the stream programming model, where it's a producer-consumer model. At the center of this model is this concept of stream registers, and we'll talk a little bit about that, because that is a core concept. Instead of routing packets, we're routing stream registers, and that's kind of a critical concept. And then we'll talk about basically how the instruction fetching and dispatching works across these tiles. As I mentioned, this central hardware structure here is this concept of a streaming register. And a streaming register is similar to a general purpose register in that when you're loading, you load a memory content from the memory into a general purpose register, and then like any other RISC architecture, you have a ALU that operates on those registers. And we can load multiple operands in the registers at the same time to accomplish essentially what is a tensor assembly line flowing eastwardly and westwardly on the chip as data moves on the chip. One of the things that's unique about this is that each stream here is 1 byte wide, and that 1 byte wide comes about by kind of that fundamental data type. The chip is designed to operate on tensors. Tensors are a multi-dimensional array of the same type, and the fundamental type that we operate on spans from int 8 up to FP16 and FP32, for example, in the vector units. So these stream registers are different than most general purpose registers. If you've ever programmed on a MIPS architecture, for example, and you load some register R1, for example, with the contents of memory, and you can come back 2 weeks from now and the contents of register R1 will still be the same if you haven't overwritten it. In this architecture, it's a little different. When you load a vector into this streaming register, it becomes a stream, and that it literally starts flowing on the chip. So memory semantics for the chip have a direction associated with them. So for example, when you do a vector load from memory, it has an east or west direction to it. In other words, that first hop on the on-chip network is specified in the instruction to indicate which direction that stream is going to flow on the on-chip network. And one of the things that you'll notice is that these are 16-byte chunks, and these 16-byte quantities corresponds to the specific lane that the data is associated with. So this concept of a parallel lane is the data abstraction on which the architecture is built, on this 320 lane abstraction. So vectors are essentially 320 elements as a maximum vector length, and that allows us to strip mine our tensors onto this long vector length and take advantage of the benefit of SIMD execution. So the architecture provides 64 registers, that's 32 east and 32 west. And as we walk through this, I just want to point out that this is the basis for this assembly line. It's really across the chip, we've got these flowing registers that flow east and west, and we can take advantage of these streams as data is flowing across the different functional units. I'm going to pick up the data, operate on it, and then put it back into the stream, stream registers where it continues on. So in this way, we're able to take advantage of the data flow locality. And I'll talk specifically what I mean by data flow locality, but there's a couple of things that are really important that I want to emphasize. First of all, one thing that's unique about this on-chip network is that there are no headers, in that we define our on-chip network entirely through a deterministic time and space algorithm. So in other words, we know precisely the time and location of tensors as they flow across the chip. And we can do that because we maintained a simple property of determinism in the design of the ASIC. By determinism, I mean in a very concrete sense, we do not have any reactive hardware components, such as an arbiter or replay, reliable replay mechanism, like in a link layer, for example, that would cause event orderings to be perturbed in a way that the compiler would not be allowed to, or could not reason about correctness. So the idea here is that we're building a deterministic data path that the compiler can completely predict on a cycle-by-cycle basis exactly what is happening on the chip. To accomplish that, the compiler must start with taking these higher order or higher dimension tensors and lowering them to a rank 2 tensor. And rank 2 specifically is where the hardware implements this abstraction of a tensor, and it represents that rank 2 tensor as kind of a vector over time. So you can think about tensors that are flowing on the chip. They have a certain spatial dimension. They have a certain vector length. And that vector length is essentially the inside dimension, the inner dimension of this rank 2 tensor. The outer dimension is the streaming time, or a temporal dimension of how long it takes to stream that data across that functional unit. So those are kind of the 2 dimensions of the rank 2 tensor as it flows on the chip. And we're able to exploit that in a way that allows us to route tensors on the chip without having any packet overhead for headers. In fact, the only overhead we have is for ECC protection. So a little bit about data flow locality. The basic idea of this architecture is that we have a single superlane which embodies all those components of a chip core. For example, each superlane has all the core elements of what is our homogeneous core. In other words, it's got the integer floating point ALUs, it's got some data manipulation, it's got some memory storage, a vector unit for doing fixed point-wise operations. And we're able to take advantage of this locality as data flows on the chip. For example, we use this to construct essentially micro programs that are constructed from these different instruction control unit programs that are flowing on the chip. And these instruction control units are feeding instructions to these functional units in a northwardly as it dispatches instructions. So you can think of data as flowing east and west, and instructions are flowing north and south. And where the 2 intersect, you have the opportunity to do a computation, and that computation performs some operation and puts the result in the streams. And so as an example of this, we're able to read some register or load some value from memory at time 1, and it starts flowing on the stream registers toward the VXM. The VXM is our vector processor on the chip. And so as it passes the vector processor, we want to pick up the elements and add a bias to it as they flow on the chip and continue to flow past what's called our SXM, or our switching unit on the chip. And it's this switching unit that allows us to permute or rearrange the elements of a tensor before they finally get deposited or loaded into the array for the MXM, for this matrix array that we can do a large matmul, for example, or convolution and extract features. And then we can take those extracted features and then write those out to memory to save them for later retrieval. And so this is the idea of chaining together these different functional units, these different functional slices in a way that exploits the locality and takes advantage of this kind of functional unit chaining so that we can take the output of one functional slice and feed it to the input of the next slice and avoid writing the intermediate results back to memory. This is not only very power efficient, it's very energy efficient. So that's the idea behind this streaming model. And each chip, like I said, maintains this 320 lane programming abstraction, which is implemented by each superlane. Each superlane implements 16 elements of this 320 element vector. Okay, so the way to think about this is each of these superlanes is producing 16 elements, and there's a total of 20 superlanes on the chip. 20 times 16 is 320 for a maximum vector length of 320 elements. Okay, and again, that's arranged as 32 eastward streams and 32 westward streams, and that is really the centerpiece of the on-chip network, is that data movement in the XY direction. I'm sorry, in the X dimension, in the eastern western dimension. And then lastly, at the center of all this is the architecturally visible state, which includes the globally shared SRAM, this large 220 megabyte scratchpad SRAM that all the functional units have uniform access to. So let's take a look at this and plumb into this a little bit deeper. And one thing about this talk is I'll try to punch into details and then pop up and look at general concepts and then dive back down into details to try to reinforce them. One of the things that the architecture is built on is, like I said, is this concept of superlanes. And superlanes allow the instructions to flow north and the data to flow east and west. And again, the idea here is it allows us to exploit this data flow locality as instructions execute and flow and dispatched on the chip from south to north. They're executed cycle by cycle in a pipelined way that allows us to really extract a lot of value from the underlying silicon. In particular, we're able to extract over 750 teraops of performance from this silicon. That's over 1 teraop per second per square millimeter. And that's what we're really excited about, is being able to have an architecture that provides a bandwidth-rich substrate from which our customers can extract a good performance for their machine learning models or high-performance computing models. So tensors are basically a vector in time that allows us to represent data as different data types. And specifically, the hardware supports either signed or unsigned int8 values for quantized models. So you can take advantage of these lower precision models, or you can do training or inference in float 16. So we support half precision IEEE for inference as well as training. And like I said, the core here is really structured around this concept of tensors, and as data is flowing on the chip, how do we keep these vectors moving in time to stream it across the functional units? So as part of the on-chip network, the on-chip network really satisfies one fundamental idea, and that is data reshapes. And if you've worked in machine learning for a while, you know that there's a lot of tensor reshapes that happen as part of moving from one layer to the next as tensors are operated on. And so our switch execution module, or SXM, implements the necessary ISA support for very common tensor operations. And these include an in-memory transpose that does a 16 by 16 transpose to take 256 elements and kind of rearrange the rows and columns very efficiently. It includes rotations to be able to rotate data elements within a vector, or shifting them up and down. And more generally, we're able to take and permute the data and distribute that data in a very efficient way to take advantage of it. At the center of this on-switch network is our SXM, like I said, and that implements actually a Benesch folded CLO. It's actually a hybrid switching network here that software has complete control over the configuration of and permutation mapping between input vectors and output vectors. So the software sets up the permutation map, and then we're able to stream vectors across this on-chip network to be able to rearrange and permute the elements within a vector. And as you can see, the chip is very symmetric, and there is a SXM in the East Hemisphere as well as on the West Hemisphere. I'm only showing one of them for purposes of simplification, but you can see that this is a very wire-dominated portion of the chip, and this is what effectively allows us to do very efficient data reshapes on those tensors. In addition, we have a vector processor that sits at the center of the chip, right at the chip's bisection. So we have the largest amount of bisection bandwidth coming into that functional unit. So you can think of, we've got these memory units, these memory hemispheres, and each memory unit delivers 32 streams times 320 lanes, which is 10 terabytes per second of on-stream of stream bandwidth. And so we've got 10 terabytes per second coming from this direction and 10 terabytes coming from the other direction. And so this vector unit sits right at the bisection of the chip, and we're able to take advantage of all this operand bandwidth and use that very efficiently. In particular, we have a different arrangement, a different on-chip organization of the functional units in the vector processor than what we did, for example, in the SXM. So the idea here is that we're able to leverage a common movement of data in the X dimension, but the different functional units want some freedom to be able to have a different data movement in the Y dimension. So for example, this arrangement of ALUs allows us to very efficiently construct chained operations between the ALUs. So for example, very common operations that use will convert from floating point to integer, or integer to floating point, and do a multiply and scale data and then add, for example, and then do a ReLU. And you can do that by chaining together these different operations in the ALUs in a very efficient and straightforward way. And just to point out the different types of data flow on the chip and how they vary from one functional unit to the next. So the SXM, as I mentioned, is our switching unit. The vector unit is our vector processor, and the matrix unit, or MXM, is our matrix unit for deep learning operations. And that does a 320 by 320 operation, and these operate on tensors. And you can see as part of the data, we've got an input weights, we've got input activations, and we produce an output feature. And you can see that there's very carefully choreographed data flow or data movement, and we're exploiting this data movement in the functional units to make the functional units very, very efficient for those types of operations. And in other words, if you look at this array of multiply accumulators, we're using it in a very fixed function way to be able to produce outputs in a very controlled manner. So the data flow requirements really guide how the on-chip network is being used in this portion of the chip. So let's pop up a little bit and look at just the summary of the on-chip network as we talked about it is really guided by these high bandwidth on-chip streams that are streaming on the chip. And the different functional units that operate on those. The VXM uses this 2D mesh of ALUs. The SXM uses a permuter network, which is actually a Benesch folded Clos hybrid switch, 320 inputs and 320 outputs. And the MXM, as I mentioned, produces this fused dot product of the 320 elements in a very controlled and precise way. And we use this very, very specifically to create this assembly line of tensors around which we've organized them as rank 2 tensors. So that kind of describes the on-chip network and how we take advantage of different kinds of communication patterns on the on-chip network to be able to exploit and efficiently expose and use the parallelism on the ASIC. Now, as I mentioned, one of the things that we wanted to take advantage of was the abundant on-chip bandwidth, and the reason we want to do that is because we want to be able to drive our off-chip links. That is the ability to connect up multiple of these chips into a larger system and do synchronous communication across the system. So the goals here was to provide a mechanism that uses the wire density at each level of the packaging hierarchy. So not only within the chip, but on the card, and then within the node, and then the racks from which those nodes are constructed. So there's a packaging hierarchy that really dominates the interconnect topology and the routing of how routing is performed. And so the topology and routing and flow control are the principal determinants of your system performance in the on-chip or the off-chip network. And so one of the things that I wanted to emphasize is we're really focused on low end-to-end latency, so a low diameter network. We want to be able to build as large of a system as we can and keep the diameter very low, because we're gonna keep the chips in the system in a pseudo-synchronous way. So we keep them all kind of in synchrony by adjusting the skew that may have accumulated over time. So it's kind of similar to kind of Lampert logical clocks. We have a distributed system, and they're all running kind of, these plesiochronous links are mostly synchronous, but their synchronicity varies a little bit in terms of the tolerance that the crystal that's driving them admits. For example, the crystal oscillators that drive our clocks on these systems are generally about 50 parts per million of drift. So over the span of 1 million cycles, you could get some amount of variance in that clock. And that's what we do, is we basically de-skew the clocks across the system to keep a perfectly synchronous system. So as we talk about this packaging hierarchy, I want to be able to walk through and talk a little bit about the on-chip network, which we addressed already, and how we build cards from that, and then how those cards fit into a node. and that node fits into a broader system or a rack of systems. So on the outside of the chip, you'll notice that we have these blocks here called the C2C links. These are the chip-to-chip links, and there's a total of 16 links around the edge of the chip here, and these are what we use to create glueless multiprocessors. In other words, we can build direct networks to connect up multiples of these chips without any additional switches. Okay, so if we look at the amount of off-chip bandwidth, we have 16 links, each operating at 30 gigabits per second maximum speed, and they're 4 lanes wide. So this gives us almost 4 terabits per second of on-chip memory. If you include the Gen 4 PCIe, it's about half a terabyte per second of off-chip bandwidth, from which we, again, want to expose and use this direct interconnection network to create low-cost networks. So one thing that's different about this communication model from traditional models is in a traditional multiprocessor, you've got this very well-defined request-reply communication protocol that a requester sends a request to a node and asks for a address, say X. And the respondent will do a memory reference and get the data and then send that back to the requester across the network. And this is a very common request reply kind of protocol. Unlike traditional networks, however, the Groq network is software defined and its compile time, we know the traffic pattern at compile time, so we can literally short circuit this by providing the reply data at the exact moment it's needed when the operand is needed, for example. And the way that we do that is by scheduling these send and receive, explicit send and receive calls in time. So they have a specific timestamp on each send and receive. So this is similar in concept to how MPI explicitly uses send and receive to do these pointwise communications. However, again, the concept here is that we've got a timestamp in front of every instruction that says when that instruction is going to execute, and the compiler is the thing that organizes and orchestrates those timestamps to make sure that everyone is communicating at the right time. So at the basis of this, we've got 2 nodes, A and B, that are communicating across some channel with a fixed latency, and we represent that fixed latency as just a fixed delay, and we schedule that in software, entirely in software. Okay, so the nodes are set up in the system to take advantage of this logically shared but physically distributed memory. In other words, the system aggregate system memory is logically shared across all the TSPs in the system, and we're able to take advantage of this and exploit it and to use it for model parallelism across the TSPs of the system. So if you look at the different elements or dimensions of this parallelism across the chip, we can see the different components of it. At the largest or the most granular sense, we've got TSP chips. And there's multiple TSP chips in the system. Each of them is divided into East and West hemisphere, and each hemisphere has 44 slices, and this 44 slices represents the amount of bank concurrency or memory concurrency. And then we use that as essentially our unit of concurrency around which we build concurrent algorithms. At the next layer up in the packaging hierarchy, we have the node organization. And in this case, we organize multiple TSP chips into a 4-way node. And these nodes are connected internal to the chassis. So the cables are hidden. You won't see these internal connections. And we take advantage of the fact that things that are closer together are able to be more richly connected. This notion of packaging locality, that things that are close together can have shorter wires and therefore have faster wires, and these operate at all 30 gigabit per second and 4 lanes wide. And again, we have more internal bandwidth within this node than what we have going to the external nodes. And the host system in this case is a AMD Rome system, and that Rome system has 160 lanes of PCIe lane Gen 4 PCIe bandwidth. It's a tremendous amount of I/O bandwidth that we're able to put to direct use with the Tensor Streaming Processor. We package 8 of these into a single chassis, a single 4U chassis, and we're able to densely package those to be able to build a very computationally dense node that we fit into a larger rack scale system. And this rack allows us to very densely interconnect all the nodes within the rack using electrical and specifically passive electrical signaling. So we're able to take advantage of low-cost electrical signaling within the rack. In other words, where you're communicating a short distance on the order of 1 to 2 meters, 1 to 2 meters within the rack, you're able to communicate using conventional electrical cabling. For longer reach, we also support active optics cables. So these are QSFP cables. We're using commodity interconnects, and that was one of the goals of the off-chip network, was to be able to leverage commodity cables, so we don't have to build a custom cable, because that becomes extraordinarily expensive when you have to start building custom cables. In each node provides a virtual router providing 16 global ports that are used to fully connect the 16 nodes within a single rack. Okay, so we use this concept of packaging locality to exploit that and take advantage of the tremendous amount of off-chip bandwidth that we have, and provide a rack, a single system rack, that has 48 petaops of int8 performance. So if you're using quantized models, and 12 petaflops of FP16 performance, all within a single shared memory capacity of around 14 gigabytes in the rack and 3.2 terabytes per second of bisection bandwidth. Again, the other concept here is low latency from end to end. And we wanted to be able to provide low end-to-end latency to be able to give good collective support and be able to operate on the time scale of about 1 microsecond from end to end. So hopefully I've kind of motivated and walked through both the on-chip network, some of the technology drivers driving that on-chip network, and really it's all about extracting as much value from the ASIC wire density that we can. We have roughly, in 1 millimeter on the ASIC, we have roughly 10,000 wires that we can expose. If we look at that in comparison to the off-chip network, where we're trying to build high-radix routers and direct networks to be able to efficiently connect larger systems, all this needs to be done in a way that maintains this notion of determinism. So one of the trade-offs that we had to look at was, how do we provide reliable link transmission across the off-chip links? In other words, from chip A to chip B, we don't want a transmission error to be replayed or retried. So we wanted to use forward error correction, because that allows us to maintain determinism across the system. In other words, we don't have to account for any error or exception handling that would go across a retry mechanism. With that in mind, I want to say thank you, and thank you for joining. And I encourage you to visit the website, and we are hiring. If there's